Hello and welcome. Today we're going to explore a beautiful and powerful idea in mathematics called the integral. Now, that word might sound a little intimidating, but I promise you the core concept is something you already understand intuitively. At its heart, an integral is just a way of adding up lots and lots of tiny little pieces to find a whole. Imagine you have a pile of sand. You could try to measure the whole pile at once, or you could measure it one tiny grain at a time and add it all up. Integrals are like that second approach, but for things that are constantly changing, like the speed of a car or the height of a curving hill. It's a tool for summing up continuous change. Let's think about a simple question. If you have a rectangle, how do you find its area? You probably said length times width. It's straightforward because the height of the rectangle is constant. It doesn't change from one side to the other. But what if the top of your shape wasn't a flat straight line? What if it was a swooping, graceful curve? Suddenly the height is different at every single point. You can't just pick one height and multiply it by the width. This is the exact problem that integrals were invented to solve. They give us a precise method for finding the area of these complex, curvy shapes. Alright, so we have a curvy shape and we want to find its area. Our trusty length times width formula doesn't work directly. So, what can we do? We know how to find the area of a rectangle. So, let's try to approximate our curvy area using rectangles. Imagine our curve is drawn on a graph. We could draw one big wide rectangle under it. The height of this rectangle could be, say, the height of the curve at the midpoint. Now, if we calculate the area of this one rectangle, will it be a good approximation of the area under the curve? Probably not. Parts of the rectangle will stick out above the curve, other parts will leave gaps underneath. What's the logical next step to get a better approximation? Well, what if we use two rectangles instead of one? We could split our area down the middle. Now we have two narrower rectangles. We can adjust the height of each one to better match the curve in its own little section. If we add the areas of these two rectangles together, our total is going to be a much closer estimate of the real area under the curve. The gaps are smaller and the parts that stick out are smaller. We're getting warmer. This is the fundamental strategy. Divide the problem into smaller, manageable pieces that we know how to solve. Now, let's take this idea to its logical conclusion. If two rectangles are better than one, what about four? If we split the area into four sections and draw four skinny rectangles, the approximation gets even better. The combined area of these four rectangles will be very, very close to the true area we're looking for. The little errors, the gaps and the overshoots, are shrinking. You can probably see where this is going. What if we